Today we are going to take a look at addition and subtraction of whole numbers. Turn that volume up. And we're going to kind of use 3.1 and 3.3 as ways to establish the concepts. And then, so they're going to feel very similar, and then 3.2 and 3.4 are going to feel very similar as well. So you're going to sort of feel like we're repeating the same process here in a couple of days, but with a different operation. So let me start with a definition for us. Goodness, hang on, let's move that over. All right, we'll try it from here. All right, so we're going to let A and B be disjoint finite sets. We've been talking about sets in chapter 2. We've done Venn diagrams, we've done this set notation with the curly braces and different ideas with that. So they're different disjoint. Do you know what disjoint meant? What does disjoint mean? Excellent, we just had testing. I'm pretty sure it talked about things like this on there. Disjoint means that they are completely separated from one another. They don't have anything in common. Okay, mutually exclusive was another phrase that you may have seen me talk about at one point. Excellent. All right, so they're disjoint, they're separated from one another. And we know that the number of items in set A is little a, and then the number of items in set B is little b. And if we want to talk about what these numbers A plus B are, what they really are is they're really the number of items in the union of A and B. But because the union, because the intersection contains nothing in common, they don't have anything to overlap, that ends up simply being the number of items in A and the number of items in B. That's why we get the A plus B on the left. Okay? A and B are called the addends. Who remembers that from elementary school? Remember addends? It's language that's come home on papers for my daughter already, so I know that they still use that. And then the result, A plus B, when we actually add those together, is called sum. All right, so we're first going to talk about example 1 says, give an example to show why in the definition of A and B, in the definition of addition, A and B must be disjoint. So I've already hinted at the issue here. What is it? What would happen if they weren't disjoint? Because that's the key here.
You would be adding the same thing twice.
Right, so let's say, for instance, can I draw a picture to have a picture of that? Let's say we did have them legitimately overlapping, like in our Venn diagram pictures. So they had something in common, that is, they actually weren't disjoint. So there's some number in here, there's some number here, and there's some number out here. Let me do 8, just so the numbers are different. So we'll call this set A, this set B, and we have something like this. So this is my example that I'm creating. I could create this with a list of numbers just as well. Okay, I just chose a picture. So how many items are in set A? 7. Very good. Why not 5? We have to include the overlap, and that's part of the circle A. So then how many items are in circle B? 10. So if I were to use this definition, this would be little a, this would be little b, and what happens when I add a plus b together here? I get 17, and the problem with that is that's not the number of items in the union. What is the number of items in the union of these two sets? How many? 15, yes. 15, and these two are clearly not equal. So this will work, however, if the two had not been here. If the two had not been here, and we could sort of separate the circles away from each other because there wasn't anything in the overlap, we would have been able to add these together, and they would have been the individual, or it would have been the same as the sum of the union of the two objects. So that's what's going on with that idea of being disjoint. It really needs to be disjoint in order for this to work. All right. What we're going to look at next is different models for addition. So some of you might simply think, well, in fact, most of you probably do, all addition is adding two numbers together. Well, what we're going to see between addition and subtraction, both in this section, multiplication and division in section 3.3, is that the different models sometimes create the problems for the students more than simply the addition of doing so, like the actual computation. It's the model that's causing the problems. So let me talk about the first model for addition is the set model. So this is typically used for whole objects, and we are doing addition and subtraction of whole numbers, so that makes sense here. And here's an example of a model that would work for an example of a problem that would be a set model. Liz has 3 blue crayons and 2 red crayons. If she combines all the crayons, how many crayons does she have? So these are disjoint objects, right? The crayon is not both blue and red, so we don't have to worry about the disjoint issue. And so picture-wise, if you were drawing a picture of this, or if you're modeling this in a concrete way, we could actually draw this. So I'm going to use this, and I'm going to draw, how many, what does it say? 3 blue crayons. So I'm going to fill this in with blue, and I need more of these. I need 3 of them, in fact, right? There I have 3 blue crayons, and I have 2 red crayons. Okay. 2 red crayons. So I've got these 2 sets that I'm going to then combine together. So these are basically 2 different sets. This is, for instance, set A. This can be thought of as set B. And if we're going to combine them together, then the result will be the same picture that I already have, but all combined into the same set. So here's 1, 2, 3, and the result is, of course, 5 crayons. So this is sort of the picture that would go with a set model. You can actually physically draw it most of the time, okay? Next one's actually different. The next one's called a number line or a measurement model. And it's typically used for objects that can be broken into pieces. And I mean, I recognize that the crayons can be broken into pieces, but that's not usually what we think of when we think about the crayon, right? If I talk about having a crayon, you don't know how big the crayon is, you still call it a crayon. Well, this one's different, right? Because we have 4 feet of wood in one case, and we have 3 feet of aluminum in the other case. This is actually measured in feet. And while I'm working with whole numbers, 3s and 4s, it is something that we could actually talk about half of, and we could think about it in that way, right? I could talk about a half a foot of wood, right? 6 inches would be about like this. And it makes sense to us to think about it in that way. So this is a measurement model. To do a measurement model, we can do that on a number line. I'm just going to draw the number line in the positive sense, in every bit as much as because we're only using whole numbers anyway. So this is 0 is where we're starting. And then I've got 4 feet of wood. So I could actually, in fact, I'll draw it out here. 1, 2, 3, and 4. So my piece of wood that I'm going to draw could actually be drawn right here. And it's 4 long. Okay, I apparently don't have, well, I'm going to make my wood gray because I don't want to have to worry about finding the brown. And then I need 3 feet of aluminum. So here's 3 more. And we can put them, oops, hang on, move that back. We can put them end to end because our question is not actually how many pieces of this object we have, it's what the length is of the 2 objects combined. Do you see the difference? I'll do this lighter shade of gray just for fun. All right, so there's my aluminum. All right, so if I actually count out, here's to 4, and then 3 more, I'm to 7, so the answer, of course, is 7 feet. This one up here was 5 crayons. So we're counting something different. Instead of counting the number of objects, which is what we did on the first one, we're counting, in this case, how long the objects are. That's something different. It may not feel very different to you, but you've been adding for 10 years or more, right? More. Like 12, 16, I don't know. We're close. We're close. A long time. Your students haven't. All right. So that's the first 2 that we're going to start with here. There's far more models for subtraction that actually cost students much more difficult than the addition ones. But let's take a look at a couple other ideas in regard to this concept. So the first one is the definition of less than. So if we have two numbers, A and B, we can say that A is less than B. And we write it with the notation right here that you've seen before. If and only if there exists a natural number k such that A plus k equals B. Now, you know this, even if this sort of looks like a strange way to define it. All this is saying is that the reason that 2 is less than 5 is because I could add the number 3 to 2 and actually make it equal 5. That's all that definition is saying. Is there something I could add on the left-hand side that would make the two sides the same? There exists a number that would make that work. So this is, and it's a whole number. That number 3 has to be a positive integer. It has a positive in order for this to work. So this looks a little bit different. Example 2 says we're going to give a definition. So definition means it's going to look very much like this. We're going to write a lot of words down. But we're going to use the object, or use the definition of less than using subtraction in the definition instead of addition in the definition. So the first part is going to start the same. It's going to say for any whole numbers A and B. Okay? A is less than B. Written same way as before. If and only if there exists a natural number k such that what? I'm not supposed to have an addition statement. I'm not supposed to have A plus K equals B and make this work. What should I have instead? I can take the K and I can actually subtract it from the larger value instead, right? So we can actually write that, and just to keep the order the same, I'm going to write it like this. A is equal to B minus A. Right? And with the numbers that I used before, of course this makes sense. If I had 2 less than 5, this is what we mean by less than, because I could actually take the number 3 away from 5, and I could end up with a 2 that's on the other side. So we can define it either direction, and it makes sense. This is what we mean by less than. All right, so we're about to start properties, and these properties that you see are going to extend from now until the end of Math 2. So we're starting now with whole numbers, and we have a bunch of properties. The first property is the closure property. The closure property says that if we have two numbers, A and B, and we add them together, because we're working with addition, then their sum, A plus B, is a whole number. Hopefully you're saying, yeah, so what? Right? You knew that. You add two whole numbers, you get another whole number. Well, that sounds like an easy idea. The problem is it doesn't always work that way. So let me give you an example so you can see that doesn't work. Let's say you were talking about legitimate fractions, that is, fractions that cannot be turned into whole numbers. Okay? Talking about the numbers like 1/2, 2/3, and 6/9, and these numbers. And we can simplify them perhaps, but they don't turn into whole numbers. I can't always add two fractions together and get another fraction. That is a fraction that doesn't turn into a whole number. Right? If I have 1/3 and I add 2/3 together, what do I get? 1. It doesn't still look like a fraction that's unable to be turned into a whole number. So this is very specific, and it doesn't work for every set of numbers. But it does work for whole numbers. You add 5 plus 6 and you know you get another whole number 11. Does this make sense? One of my colleagues once described it this way, which I thought was a really good description, because we're going to keep coming back to this idea of closure. So imagine in this room, you have the whole numbers, and they're floating around above you like little bumblebees. Okay, got all the little floating bumblebee numbers. So you've got 5, and you've got 5,000, and you've got 422. You don't have some things. What don't you have? Fractions, decimals, negatives. Good. I was hoping somebody said you don't have negatives. We don't have pi or irrational numbers like square root of 3. So the only thing that we have in this room are those whole numbers. And we've got 0. We do have 0, yeah. The 0 is a whole number. Okay, so they're all floating in the room. If you've got an operation that's closed, it means that when you take those two objects from the corners of the room and you add them together, their sum is still a number that's in this room. That is, I don't have to open the door to get the result. Because all the other numbers, they're waiting outside. Can you picture that? See, that didn't happen when we had those fractions, right? We had all those fractions floating around in here and we added the 1/3 and the 2/3 and we combined them. That object, when they were combined, is not in this room. It would be outside the room. Because those two objects, that description was all those legitimate fractions that can't be simplified into whole numbers. That's how I described it, right? But when I combined those two, it didn't fit that description anymore. I have to go outside the room to get it. So that's the idea of closure. All right, let's do the next one. The next one's commutative. Do you guys remember what the commutative property is? That's right. All right, so if you have two whole numbers, it does not matter the order in which you have them added. Oops, get the addition sign in there. Again, you know this. If you've ever worked with small children in flashcards, kids do this all the time, right? They don't really, at some point, have to add 9 plus 6 and remember the 9's tables for addition, because they already learned 6 plus 9. Right? Okay, so it doesn't matter the order in which you add. That's the commutative property. What's the associative property? First of all, it's missing a piece. I actually need we'll just write it in here, A, B, and C to use the associative property. I need 3 objects. So mark that out. You're close. That's the distributive property. So we want something that only uses addition. So we're not going to get to the multiplication part yet. Well, we will on Monday next week or Tuesday, Wednesday this week. Get to multiplication. We're not there quite yet.
Isn't it A plus B equals B plus C, then I'm saying right, then A plus B equals B plus C, then that has to be equal to C plus A or something like that?
You're getting close. You're getting close. No subtraction yet. We're only working with addition. You guys are so creative today. All right, let's take a step back from this, and I want you to think about what the word means. What does the word associative mean? And let's actually take it to a simpler form. What does the word associate mean? What does it mean to associate something? Put them together. So if I ask you who you associate with, it's the people that you kind of group together with, right? People you talk to, people that you kind of congregate with. Associative property has that feel to it as well. What it does is it says that if I add two numbers together and I associate them, and then I add a third member to that grouping, that I would end up with the exact same result if I had associated the other two members together first. I get the same group of people, right? So if Nicole and Becca came to class and then Amanda comes in, it's the same 3 people no matter how they showed up, right? They all 3 got here. Same thing here, but we're talking about addition, of course. So this works with addition. We can actually group things together in any order and this addition will still work. That's a really cool thing. And the reason that's so helpful is because there are certain numbers that are more helpful to add together than others. For instance, if you had, you know what, let me use a different color. If you had 5 plus 2 plus 8, there's nothing difficult about those numbers. I'm not arguing that. But I will argue that it is easier to add the 2 plus 8 together and then the 5, especially if the numbers get quite large. Why? Tens are easy to add with, yeah. And so it's really a nice nice fact that I can change the order of my grouping however I like so that my addition is easier to work with. This is a great thing. You use it probably more than you realize, and you didn't know you were doing it. It's called the associative property. The last one is the identity property, the additive identity property. That's important to remember because additive and multiplicative identities are different things. The additive identity property says there is a number, and that number is the matrix 0, but when you add it to something, it doesn't change the value. Right? You guys know this. Everybody loves when they add the numbers together when they're little kids and they've got a multiplication table and a multiplication flashcard that says something plus 0. Alright, but it didn't change anything. So that's the additive identity property. Alright, so what we're going to do in the next slide is we're going to take a look at some of these properties and we're going to identify which one's being used in which situation. Okay? So the first one, what property is that? It's which one? Commutative, right. I've changed the order of something. And it's actually kind of what we mean by the word commute, right? When we talk about commuting to work, it means that I go to work and then I go from work back home. It's a commute. I change my order of where I am. So this is the commutative property. How about the second one? It is. It's the identity property, right? Because it's this plus 0 fact that I actually ended up with the same 6 plus 3 that I started with. So this is the additive identity. Please make sure you specify. Because right now, that's the only identity we have, but that's not going to be true for very long. The additive identity. How about C? No, but look again. Which one is it? So I've heard associative and commutative and merely wanted to say both of them. It's one or the other. Which one is it? It is commutative. Associative changes the numbers that are in the sets of parentheses. This didn't change. I have 6 plus 8 inside of both those parentheses. What actually changed was the order of the 6 plus 8. So don't just think, if I see parentheses, that's associative. It is not true. So this is the commutative property again. How's the last one? That is associative. The numbers are actually different, right? This is a 5 plus 3 inside this parenthesis, and this one's the 3 plus 2 inside of the parenthesis on the right. So this one is the associative property. Any questions on those? Okay, so we're going to look at a couple of strategies for addition. Four properties. First one is counting on. So the counting on property says what you do is you can start with a lower value, you can start with a higher value, and you're counting after that value. So I've seen children do it, and I know that I did it too when I was a child, right? So if you wanted to do 5 plus 6, you could actually say, I'm going to take one or the other number, I don't care which one it is, and it really doesn't have to be smaller. Let's say it's 6. And we go 7, 8, 9, 10, 11. So I counted 5 more on top of the number 6. That's counting on strategy. Okay. The next one is a doubles strategy. And this is actually one that's taught frequently in the schools as well. It's the idea that if you know the doubles, or you have something that's nearly a double, you can use the fact that you've got doubles. So if a student knows how to double something, 3 plus 3 is 6, they can think of 3 plus 4 as a near double. So 3 plus 3 is 6 plus 1 more, so it's 7. Another strategy. Making 10. I already mentioned this one, didn't I? This idea that if I were able to look at the numbers in a different way to make 10, it's sometimes helpful. So again, we're dealing with small numbers here, not because I don't think you can handle the large numbers, but it's easier to see what's happening with the small numbers. However, you're using them more frequently when you get to the larger numbers. Okay, so I'm just using the small numbers as an example. All right, so if you had 8 plus 6, and you're working with that, or some other variation of this, you could break the 6 apart into 2 plus 4. That's what's happening here. So the 6 became 2 plus 4. And the reason that might be helpful is because if you start with 8 and I add 2 to it again, I get that 10. And then the leftover piece 4 would be added to the 10 when I'm done. Getting 10s are nice, right? Well, they're good because we work with them really easily. It turns what looks like a 2-digit number into feeling much more like a 1-digit number. last one is counting backwards. Counting backwards, starting with a higher value and counting back to the lower value. This one's actually a subtraction strategy. I'm not sure how it ended up on here, but that's okay. We'll put it in here and write down that this is subtraction. So this kind of has the same feel to it as an adding on strategy, but for subtraction. So if you were doing something like 12 minus 4, you can start with the 12 and you can count backwards, 11, 10, 9, 8. Right? So you're counting backwards instead of counting upwards. All right, I want to show you the subtraction models, because this is where the models become really interesting. They are very different from one another. However, the values in them may be quite similar. All right, so for any whole numbers, first of all, into the definition, for any whole numbers A and B, since that A is greater than or equal to B, then we can talk about taking a value that is smaller than the value we're working with and subtracting it, and we will end up getting another whole number. Okay? So if we were talking about, for instance, 9 and 2, I can talk about 9 minus 2 because 9 is bigger than 2, and 9 minus 2 would then give me another whole number, 7. Okay, so that's what this is referring to. And it works in such a way that, let me use those same numbers, 9 and 2, just for fun. So then 9 minus 2 is the unique whole number 7. And the reason that it's the unique whole number 7 is because 9 is equal to 2 plus that elusive 7 that was our solution. And that is often how subtraction is first presented to children. What the question is well, what does subtraction mean? Well, if I want to do 9 minus 2, the question is, well, what do I have to add to 2 to get 9? Because you can turn it into something they already know. The question is simply what's missing. Right? So the first model is a takeaway model, and this is the one that people usually use. So this is probably the most common one. Abby had 24 rocks. Eli sneaked into her room and took 5 of them. What's it say next? Oh yeah, how many rocks does Abby have now? Okay, so this is an example of the takeaway model. You actually have something that you're removing pieces away from. Okay, nothing special about the rocks, except that they do create a concrete object for us to be able to draw. So I'm going to draw some rocks. You draw your rocks, I'm going to draw mine. So here's my rock. Sure, why not? It's going to be a gray rock. All right. And I want 24 of them. What do I have? 13? There's 24. They're not on top of each other. There's 24. Okay. So I have 24 objects, 24 rocks in this case, in my daughter's bedroom. She has more than that. She collects rocks. My son walks in and he takes some of them away, which so sounds like something he would do. So he's going to remove 5 of them. Is that what it said? Yeah, 5 of them. So let's go with these 5. He removes these 5. Then we can simply count how many are left, right? And we can talk about counting them by, literally in class we would probably count them across. So just for the sake of doing so here, I'll put the numbers on them. Did I get 19? Okay. So this is 24 minus the 5 gives me 19. Takeaway model has a really concrete image. So it's the one that students tend to remember the most. Okay, you've got this image that you can talk about, I actually have something and I'm removing something from it. Takeaway model. Alright, let's talk about the next one. The next one is the missing add-ins model. So the missing add-ins model has this feel that I need something for some purpose, and I don't quite have all of what I need. Okay? I'm missing something to have what I actually need. So here's my example. Eli needs to collect 10 leaves for school project. He and Abby go out and find 8 leaves. How many more leaves does Eli need? Okay, so we can actually take our objects and we can create these. I'll make my leaf like this. Here's me a green leaf. And I'm supposed to have 8 of them. I have 8, right? But I'm missing some. I need some more to actually have 10. So I can draw a picture where if those objects were filled in green, I would have what I am actually needing, 10 of them, 10 of these objects. And the number of objects that I added to that picture to get me up to where I was would be my answer. So yes, I do 10 minus 8, but for a very different reason than I did on the other problem. This is not I had 10 and somebody took 2 of them away. This is I need 10 and I only have 8. Do you see the difference? Because that difference may not feel like very big to you, but when kids are first working with the concepts of subtraction, it can really throw them. Another way that you'll see it used inside of curriculum that you may be encountering is that you'll see somebody do something like this. They'll write an equation. Because there really is a big push at using equations at a younger age, so that the first time they see an equation written like this, they don't think equals means find the answer. But that's really not what equals is supposed to mean. Equals is supposed to mean what comes before the equals and what comes after the equals are in fact the same thing. So if I write it this way, I can fill in what's missing from the box. And what's missing from this box is the number 2. So that now, in fact, both sides are equal, and my answer is not 10, my answer is 2. Because that's the part that was missing. Okay, so this is the missing add-ins model. Let's do another one. Comparison. Jessica and Jeremy played basketball. Jessica scored 12 points. Jeremy scored 8 points. How many more points did Jessica score than Jeremy? This is not taking anything away or adding anything to something. This is not one of those other 2 models, right? I'm actually comparing 2 quantities that exist. I'm not trying to get anything more. I'm not trying to take anything away. I'm just comparing. So in terms of a picture, I'm going to use tally marks this time. So Jessica is first. Here's Jessica. And she's supposed to have 12. And then we have Jeremy. And he has 8. Now in order to compare these objects, I need to line them up, or it's not going to make a lot of sense. So I'm going to compare them by lining my 8 objects up directly underneath Jessica's line. So 1, 2, 3, 4, 5, 6, 7, and 8. So you can see from the picture that what's missing in terms of comparing these objects is the 4 at the end of Jessica's, right? She has 4 that don't correspond to anything in Jeremy's situation. So this is a comparison model. Of course, again, the answer is 4. Because there are 4 missing here. They're not missing. There are 4 that aren't compared or have no partner. I'll go with this. There are 4 that don't line up. So that's the comparison model. There's one more. This is the number line model. All right, so the number line model says the following, or example says the following. Luke drives 15 miles to the mall. As he's on his way home, his mom calls to ask where he is. He states he's coming home now. He's coming home and is now 8 miles from the mall. How far is Luke from home? So this type of a model is used kind of like with that measurement model idea from the add-ins or from the addition models. It's used when we're talking about something that can't actually be a portion of something, right? Just like the other one was feet. Remember we did the feet of the wood, the feet of aluminum? Here you see miles of driving a car. So we can draw a number line model for this. That's the right one. Or number line picture. Our picture needs to go how far out? 15 15. Okay. And then there's various ways that you can do this. I'll use an arrow. I think I've got one up here that will work. We're going to try that one. We're going to take 15 and we're going to go backwards. How far are we going to go backwards? 8. So image-wise, here is home. This is, what was the name? Luke's home. And this is the mall. And his mom, at least he's told his mom, that he is 8 miles from the mall. He's already driven 8 miles home. So picture-wise, we are 8 miles backwards. I'll change it if I didn't get quite far enough. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Ooh, wow. So kind of what's happened is we're already 15 away and we're jumping back 8. The question is, where does that put us? Where am I right here? And where am I? 7. You could count to get there, or like count up from here to get here. That is one of the counting up methods or a description of it. Or you could count backwards from 15 to get back to the 7. So here I'm at 7 miles from home. Alright, so here's what we're going to do when we start next time. We don't have time to do today. But when we start next time, you're going to get a new group work folder. In fact, I'm going to read them before you leave. And we're actually going to do a touch. What's the touch of group work in the middle of the lesson?